In this video, we're going to be talking about some general probability rules. So let's begin with the general rule for addition. So for any two events E and F, we can say that the probability of E or F equals the probability of E plus the probability of F subtract the probability of E and F. So what does that mean? It means that we're going to take the probability of E and add it with the probability of F. But you'll notice that that intersection got added twice. So because the intersection was added twice, we want to take it out one time so that it's only accounted for one time. Let's look at an example. So musical styles other than rock and pop are becoming more popular. A survey of college students finds that the probability that they like country music is 0.40, and the probability that they like jazz is 0.30, and that they liked both is 0.10. So what is the probability that they like country or jazz? So here we're going to have the probability of country union with jazz, so country or jazz. So we're going to take the probability of country, the probability of jazz, and add them together and subtract the probability that they like both, leaving us with a 0.6. So here's the process to use when calculating the union of two or more events. So if we have the probability of E union with F, you need to ask yourself, are these events mutually exclusive? Because if they're mutually exclusive, then you can take the probability of E and just add it with the probability of F. But if they're not mutually exclusive, then you need to take the probability of E, add it with the probability of F, minus the probability of the intersection of E and F. Now, in some problems, the intersection of the two events is given, like in what we just did. And in some problems, the intersection of the two events is not given. But we know that the events are independent. So if they're independent, then we're going to take the probability of E times the probability of F to get that value. Let's go through an example. Suppose the two six-sided dice are rolled, one white and one red. What is the probability that the white dice lands on a 6, or that the red dice lands on a 1? So we're going to let A equal the white die landing on a 6, and let B equal the red die landing on a 1. So we want to know, are A and B disjoint? No. So here we have the probability of A or B. So we're going to take the probability of A and add it with the probability of B, and subtract the probability of A and B. So how can we find the probability of A and B? Because they're independent events, we're able to multiply it together. So here we'll have the probability of 1 over 6 plus 1 over 6 minus 1 over 6 times 1 over 6, which is going to give us a value of 11 over 36 for our final probability. Let's move on to the general rule for multiplication. For any two events E and F, we can say the probability of E and F will equal the probability of E given F times the probability of F. Here's a process to use when calculating the intersection of two or more events. So if we have the probability of A intersected with B, or A and B, you need to ask yourself, are these events independent? If the answer is yes, then you're going to take the probability of A and multiply it with the probability of B. But if the answer is no, then you're going to take the probability of A and multiply it with the probability of B given A. Let's do an example. There are 7 girls and 8 boys in a math class. The teacher selects 2 students at random to answer questions on the board. What is the probability that both students are girls? So we're going to begin by asking ourselves, are these events independent? And the answer is no. So we want to know, what is the probability of having a girl both times? So we're going to take the probability of our girl the first time, which is a 7 out of 15, because there were 7 girls in class out of 15 students. And then the probability of this getting a girl to come up on the second one, well, we've already taken one of the girls, so she can't be chosen again. So there's only 6 girls. there's no longer 15 students to choose from. We only have 14 students to choose from. And that is going to give us a 0.2. Let's go back to our light bulb question, or our light bulb example. So a certain brand of light bulbs are defective 5% of the time. This is from a previous video, by the way, this example. So you randomly pick a package of 2 such bulbs off of the shelf of a store. What is the probability that exactly 1 bulb is defective? So we're going to let D sub 1 equal the first light bulb is defective. And then we're going to let D sub 2 equal that the second light bulb is defective. So what we're looking for here is the probability that exactly 1 defective bulb. So here we're going to be taking the probability of our first light bulb and not our second light bulb, or our first light bulb isn't, but our second light bulb is. So we're looking for that probability. So here, the probabilities are going to come out as a 0.05 times 0.95 plus 0.95 times 0.05. And that's going to give us a value of 0.095. And we're getting these values from that previous example that we did in our video on independence. So if you're not really sure about this one, then go ahead and go back and watch that independence video to be able to get a little bit better idea of where the 0.05 and the 0.95 are coming from. Let's do a different example. An electronics store sells DVD players made by one of 2 brands. Customers can also purchase extended warranties for the DVD player. The following probabilities are given. So B sub 1 is the event that brand 1 is purchased. B sub 2 will be the event that brand 2 is purchased, and E will be the event that an extended warranty is purchased. So the probability of B sub 1 is going to equal 0.7. The probability of B sub 2 is going to be a 0.3. And the probability of E, given that they bought the first DVD player, is going to be 0.2. And the probability that they bought the extended warranty, given the second DVD brand player, is going to be a 0.4. So if a DVD customer is selected at random, what is the probability that they purchased the extended warranty? So this can happen one of 2 ways. They purchased the extended warranty and brand 1 DVD player, or they purchased the extended warranty and brand 2 DVD player. So that means E is going to equal E and B1 or E and B2. So that's what that's saying in yellow right there, in kind of an equation sense. So we're going to take that, and what we're going to notice is that these are disjoint events. So we're going to be able to take the probability of E, well, in order to find that, we'll take the probability of E and brand 1 and add that to the probability of E and brand 2. So we're able to use the general multiplication rule here. So we'll have the probability of E is going to equal the probability of E given brand 1 times the probability of brand 1 plus the probability of E given brand 2 times the probability of brand 2. So let's go ahead and let's plug in our numbers here. So we know for the probability of E that we're going to get a 0.2 times 0.7, and we're going to be able to add that to a 0.4 times 0.3, which is going to give us a 0.26, or a 26% chance. This is an example of the law of total probabilities. The law of total probabilities says that if B sub 1 and B sub 2 are disjoint events with probabilities of B sub 1 and B sub 2 equaling 1 for any event E, you're able to then say that the probability of E equals the probability of E and B1 plus the probability of E and B2, which we can then write as the probability of E given B1 times the probability of B1 plus the probability of E given B2 times the probability of B sub 2. More generally, our B sub 1, B sub 2, all the way to like B sub k are disjoint events with probabilities of B sub 1, of the probability of B sub 1 plus the probability of B sub 2. No matter how many events you have, the probability of B sub k equaling 1 for any event. So this is what this is saying kind of mathematically. Notice right here, there's not another equal sign because it just kind of ran out of room, that this little plus sign would be added on over here, since we're going all the way up to event k. So take a look at those. Notice how they're very similar. All we're doing is just making it another addition. So if we had had a third type of DVD player on the previous example, we could have just added a B sub 3 here and still been able to do our problem. So now we're going to talk about Bayes' rule, or Bayes' theorem. It's a formula discovered by Reverend Thomas Bayes, an English Presbyterian minister, to solve what he called converse problems. So let's examine the following problem before looking at the formula. Lyme's disease is the leading tick-borne disease in the United States and England. Diagnosis of the disease is difficult and is aided by a test that detects particular antibodies in the blood. The article Laboratory Consideration in the Diagnosis of and Management of Lyme Borreliosis from the American Journal of Clinical Pathology from 1993 used the following notations. It represents a positive result on a blood test. A minus sign represents a negative test on a blood test. A capital L represents the patient actually has Lyme. An L superscript C means that the patient doesn't have Lyme's disease. So the article gave the following probabilities. The probability that a patient has Lyme's, actually has Lyme's, is 0.00207, whereas the probability that a patient doesn't have Lyme's disease is 0.99723. The probability that a patient receives a positive result on a blood test and has Lyme's disease is 0.937, whereas the probability that a patient receives a negative result on a blood test but has Lyme's disease is 0.063. The probability that a patient receives a positive result on a blood test but does not have Lyme's disease is 0.03, and the probability that a patient received a negative result on their blood test and doesn't have Lyme's disease is 0.97. So again, here's the probabilities that the article gave us. And Bayes' converse problem poses this question. Given that a patient tests positive, what is the probability that he or she really has the disease? So it would be written as the probability of L given a positive test. So again, it's the primary concern. It's really the primary concern in medical diagnosis problems all the time. So Bayes reasoned as follows. The probability of having Lyme's disease and getting a positive test, given that you have a positive test, is going to equal the probability of Lyme's disease and a positive test divided by the probability of getting a positive test. Now, since the probability of Lyme's disease and a positive test is the same thing as the probability of a positive test in Lyme's disease, we can use the probability of a positive given Lyme's disease times the probability of a Lyme disease for our numerator. Then using the law of total probabilities, the denominator is going to become the probability of a positive test given Lyme disease times the probability of Lyme disease plus the probability of a positive test and doesn't have Lyme disease times the probability of doesn't have Lyme's disease, which comes out to this. From here, we're ready to substitute in our values, which we have. So when we plug our values in, we're going to be left with a 0.0596, which means that there's a 5.96% chance. So Bayes' rule, or his theorem, says that if b sub 1 and b sub 2 are disjoint events with the probabilities of b sub 1, the probability of b sub 1 plus the probability of b sub 2 equaling 1 for any event, then we're able to say this formula will work. More generally, if our b sub 1, b sub 2, all the way through b sub k are disjoint events with our probabilities of each of those events adding up to a 1 for any event, we're able to say this.